Guys, I want to start here from where almost we end last class. So just to show you where we stopped. So the last class, we focused mainly on something called snow accumulation or snow drift. Two reasons in this class could be due to roof projections. An example of roof projection is a chimney, parapet, mechanical units on top of the roof. And the second reason is due to multi-level. If you have your roof is not really one level, two levels, then there should be accumulation on the lower level. So really what I ended my class is with a numerical example. You can see on my screen there is a 3D picture of the building that we would like to find the snow accumulation only at the low roof. And so this is a 3D picture to show you what's going on. From that, I created my sections in plan view. So my section here is to the right. You can see, look at my cursor. This is the third floor, and this is the second floor. And really, the whole discussion, the whole calculations will be about estimating this snow load diagram, whether you draw it on the cross section or on the plan view. That's what we're trying to do. Okay, so I guess what we said is we said because the code said you have to try three different cases. And why three? Because there could be three different sources of accumulation. Here is case number one, where the source of the accumulation is the high roof. Guys, remember, very important, the source. You have to tell what is the source of the accumulation, because as soon as you say, here is my source, then this will dictate what is my beta. So in case number one is equal to, beta is equal to 1. And then you also have to go and find what is the length of the source, what's the width of the source, and then characteristic length. You find what we call it H prime P based on the parapet height on the source. Still, we're talking about the source, and then finding the F, and then from once we find the capital F, then we go ahead and find CA of 0. You don't have to find XD for now. Please don't find XD, because simply XD is going to be a function of the maximum CA of 0 among the three cases. So, wait, hold on XD until we find all the CA of 0. Then what you do is you go to the next case where you call the case number 2, where the portion of the lower roof, only portion, not the entire. You can see I marked the portion here in almost red. So this is my portion. And again, since the lower roof or portion of it is the source of the accumulation, so this is case number 2. So we use beta equal to 0.67, and we go ahead, we find the dimension of this shaded area, and then we find CA of 0 very, very same as case number 1. But the difference is the source. What is the source? Because everything is connected to that source. Then we get also a CA of 0, it's 2.83. We go ahead and then we find the case number 3, or we do case number 3, where the source is a different portion of the lower roof as indicated on my plan to the right. Then you go ahead and you say, what is my beta and what's my length and width of the source of the accumulation. And here we go, we're able to find a third value for the CA of 0. The thing is, guys, the code says, somewhere in the code says, you know what, do all the three cases if possible. And I will show you sometimes in some cases, you'll need to do only one. Some cases you don't need to do two. I will go through this one after I'm done. Okay, so but for now, we can do the three cases because of the geometry of the roof. But I'm going to show you some geometries. Those geometries, there is no case number 3, or sometimes even there is no case number 1. I'll show you how, but just wait for a few minutes. But now what you can do, if you are able to do 3 cases, then finally you can see in the red box here, this is your CA of 0, which is simply, it's the maximum among 2.56 from case number 3, and then 2.83 from case number 2, and then 2.71 from case number 1. So what is your final CA of 0? is simply the maximum among the three, which is 2.83. Once you're able to find C of 0, now and only now you can find XD. Okay. Now, here we go. You can see XD at the very bottom of my slide is function of the maximum C of 0. It happens to be 3 meters. What this means, it means the snow accumulation will start right next to the high roof, and it will go only for 3 meters, and it depreciates as you go away from the high roof, and then it goes back to the normal, where CA of 0 is equal to 1. That's after 3 meters from the high roof. Now, something I keep saying and insisting so many times, one of the very, very common mistake is students, when they find C of 0, they think that this number is the load, the snow intensity in kPa. This is not the case. What you get so far, C of 0, is just the accumulation factor at distance 0 from the high roof. So how can I find the snow at distance 0? Here we go. You can see on my slide here, I have two numbers, S of 0, which is the snow load intensity at 0 distance from the high roof. And you can see really what you need to do is use the snow equation. However, use C of 0 equal 2.83. We get 2.59. Look up my diagram. So the load intensity next to the high roof is 2.59. So what will be the snow intensity after XD? You go back to here, and we know at distance XD, then your C of 0 is equal to 1. I'm going to box it for you. So this is the one I'm referring to. And this is the C of 0 at distance 0. And we get two different values for the snow. This value will go here. So this value will go here. And this value will simply go here after XD. Hopefully you guys are following. Okay. Any questions so far? Let me check. Let's get temperature check. Are you following? I need to hear some noise. Are you following?
Yes.
Yeah.
Okay. Okay, then let's move on. Now, what happened is, guys, is I talked at the very, very last moment on a very, very quick, and I don't know, the way I was presenting last time was not really very helpful because you don't see my cursor, which I don't know how you get what I said. But anyway, I'm going to say it one more time. So, what we discussed so far is, you can see if I go to the 3D between the high roof and low roof, there is no physical separation. It's just one building. There is no gap in between. So how about if I have two buildings, one is high, one is low, and the lower roof is at distance little a from the high roof. If this distance little a is more than 5 meters, thank you so much. We're not getting any accumulation on the lower roof. The lower roof will just function by itself. Okay. How about if the distance between the two building, or the gap, is less than a, and also less than XD? Remember, even if, let's say, for example, 4 meter, let's say 4 meter, and we have the same scenario as last example. You guys remember that we got XD is equal to how much? It was 3 there. Over there it's 3 meter. So as soon as your little building is after 3 meter, then the lower roof will get no accumulation from the high roof. But let me, for example, tell you, what if the distance is 1.5 meter? 1.5 meter. This means is less than 5. So as per the code, I have to take into consideration the drift, and also it is less than XD. So what you can see here is gonna, for example, mark for you the XD. So the XD, guys, is simply from here to there. This is your XD. Okay, the 3 meter. So if the building is 1.5 meter away from the high roof, guess what? You have to do the calculation same exactly as we've done before. And once you finalize and finish your diagram, your lower roof will only see this portion of the diagram. How about this portion here? How about this portion here? Okay, this amount of snow will just fall to the ground. So how we do it, as I said, you just have to go through all the calculations, draw your snow diagram from 0 at the higher building, and then normal at XD, and then using the geometry of this, or trigonometry, you can able to figure out this number. Remember, this number is really what the lower roof will see. How about this number here? This snow accumulation here, this will go to the ground. Okay, so just using the geometry, I think similarity of triangles, you're able to find the snow intensity at this point. Okay. Now, I said a minute ago that not every single building you will have to do case one and case two and case three. Okay, and I'll show you and just wait and see if this makes sense for you. Let me explain. So if I give you here a plan view, so this is a plan view for a building, and simply the higher roof is taking the entire the width of your building. Okay, so probably I'm not sure if I can color it, but let's say the yellow part, the yellow is the higher roof, and this part here is the lower roof. Let me ask you, do you think you have case number 3? So again, all you have to do is just go to this, the code where the code is talking about case 1, case 2, case 3, okay? And you can see here, the upper roof is not really covering the width of your building. However, it's covering a portion. That's why there could be a possibility when the wind blows in case number 3 in this direction, this area here can accumulate some snow on this side. Let me ask you, if the higher roof is simply occupying the width of your building, the entire width, like this picture here, is there any case number 3? Please let me know. I need your input, huh? Go ahead, go ahead.
I think there is none accumulation of case 3
Do you know why?
because based on my observation, because when the snow blow, then it will only accumulate on the case 2 and 3, but not in the case 3. I mean case 1 and 2, but not in the case 3.
Exactly, because the area hatched in the code case number 3, it doesn't exist because simply the higher roof is occupying the entire width of your building. Okay, are you following, guys? Are you following? Now, so you can see here, not necessarily you have to do the 3 cases. It depends on the geometry of the roof. Sometimes we do that, sometimes we don't. You have to look at the plan view of your roof, the geometry of your roof. Now, I'm going to show you right now case number. Sometimes even we do only case number 1 for a good reason. I'll tell you and it will make sense for you. Okay? So guys, watch this, please. What if I have here on this building, I have a canopy. Okay? You guys know what does mean canopy, right? Like, let's say my building entrance is from this side, and just like I'd say it, right? We have a canopy, and the canopy, for example, is hanging by a cable to the building. So let's say this is a canopy. I'm asking you, what do you expect here on the canopy? Do you expect uniform snow or expect accumulation? Please talk, talk. It doesn't have to be for Mark, okay?
Accumulation.
Okay, guys, are you still sleepy?
No, Tahar, we're paying attention, but we've just had a pretty horrible week.
Oh my God, who's saying that? Okay, tell me about you.
There.
Okay, I'm gonna stop. You know what? Stop, stop. Okay, no more concrete for now. Okay, let's couple of minutes. What is your pain? Tell me about your pain. I wanna hear you.
We just it's just we just had a lot of assignments that last weekend, and we have lots this week. But it's not that we're not paying attention. We're all paying attention. I think I can speak for myself, but I think we're all paying attention. It's just um, maybe hard to communicate.
Okay, sure. Okay, guys. Anybody wants also to talk about their pain? I'm open. I can give you. You know, we're human, right? I also am gonna talk about my pain, but you have to start. Okay. Anybody else who's suffering, like struggling?
Too many assignments.
Okay.
Like you're a good teacher. I'm not trying to kiss your ass, but we're just we're we're yeah. It's just we're paying attention. I can promise you that.
Yeah, thank you so much. You know what? Like I never had anybody for the last 7 years to kiss my ass. Like nobody. Like nobody. Like it's just like it's just because there's no point, right? Like there is no point. Like what's the point, right? Um, Anyway, I totally appreciate this, your wording, and anyway, if you want to cry, come cry to me, okay? Because I'm gonna cry to you as well. Like seriously, guys, listen, like, you know, it's not only you. I'm not trying to say that you don't do anything, or you have no load, but all of us, we are in the same vein. Every night, and hopefully you believe me, every night I like change my clothes by 10 p.m. You can see I dress formally. I work for the entire day. My day never ends at 5. It ends at 10 p.m. Some of you ask about material, like going forward, like let's say for next class, which I try my best to be ahead of you guys. We have no material like digital material, and every slide you see on your class, it doesn't take 1 minute. A single slide sometimes, yes, it takes 30 seconds for a snapshot from the code, but other slide when you're trying to make a numerical example or you're trying to put some highlight or shade, it takes some time. Even last Sunday, I work, my day ends again at 10, Sunday, not Monday to Friday, it's Sunday. Saturday, I say, you know what? I'm not gonna do anything no matter what, no matter what. Anyway, I'm not trying to cry or complain. That's my job. I get paid for that. And I'll share with you something, guys. I know that CVT, I'm not sure if you know that, CVT is one of the best programs at SAIT. Not because I'm a CVT teacher, but I felt it. I taught at U of C. I taught in Egypt. And I can tell you, our students are the best. They are really working their butt around. They work hard. But as I'm talking to some of you and say, this will pay you off. If you go to any other program in SAIT, and I had some friends in other programs at SAIT, I don't want to say names, but when you look at what they do and what they learn, it's just funny. It's just funny. Though they waste like 1 or 2 years of their lives and bunch of money for nothing. For the 2 years, yes, you work hard, but what happens in 2 years? You will be a CVT. Hopefully you feel that, okay? Anyway, I'll leave it at this, and then I'll go back to my materials. Okay. So guys, one more time, if you look at this small building, if the entrance of the building is from here, typically what people they do is they put a canopy. So the canopy, it's not really 100 meter by 100 meter, just probably a few meters by few meter to provide a shade or maybe a kind of a static for the building. But if you're really good at math, and look at how we do the calculations, you will see we start here from the size of your source. So I'm asking you, if you have a canopy, in this case, remember, I'm going to delete everything so you guys focus. So I'm going to delete all these discussions because it's not our discussion right now. My discussion is here. We believe that at the canopy, because we have a higher roof, lower roof situation, then we get some accumulation. But my question is, are we going to do case 1, case 2, case 3? If you have a canopy, I'm going to tell you, case number 3, it does not exist, because simply the canopy is only entirely is one piece, okay? And then so case number 3 doesn't exist. And then theoretically, you should be able to do case number 1 and case number 2. But I'll show you with you something, because case number 2, when we say the canopy is the source of the accumulation, look at the numbers. When the canopy is the source of the accumulation, the LS and the WS is kind of tiny. And this will give you a very little for LSE sub S, and will give you very little for F. And since F is small, so you will get a little value for C of 0. And remember, by the code, we're asking to consider the highest value for the C of 0. Okay, so even if you don't follow the discussion and you're not paying attention to the math, and you waste probably 3 minutes for doing the CA of 0 when the accumulation source is your canopy, then guess what? What you will see is, you will see what governed is the higher roof, not the canopy, because the size of the canopy. Okay, so what I'm saying here is, in general, the code asks us to do 3 cases, 1, 2, 3, but sometimes we need to do only case 1 and case 2, and some other time we do case 1 only, because we know from the math that case number 2 will never govern because of the size of the canopy. Now, guys, I know that sometimes this is very confusing, and people they say, "Oh, Tahir, you give us lots of equation, and we don't know where to apply which," because so far you've seen 2 reasons of the accumulation. And the reason why I put this slide here is to show you 2 things. Number 1, that here is a building, and you can see we have reasons for accumulation, but the way we estimate them is differently. For example, look at D1, D5, and D6, and I'm already marking D1 and D5 and D6 here on my 3D. The source here is due to multi-level. There is a higher level roof next to lower level roof, and we get accumulation in red. How do we estimate them? According to item or clause 4.1.6.5. Okay. Now, how about the drift due to roof projection? So in green, please look at the green area, which both of them, they are D2 or drift number 2. So D2 is a snow drift due to roof projection, which is parapet. How do we find those values? Simply according to 4.1.6.7. So please don't get confused. Okay. And you can see in the same building, we use those set of equation to find the red accumulation, and then we use a different set of equation, which is way simpler, to find the green accumulation. Okay, so guys, the other thing is this is a real project. What you see here is a real project. It's the Medicine Hat Police Service Headquarters expansion. Okay, so what happens here is the same for the same building. I showed you the plan view. So this is the roof plan. And on the roof we have to show our snow accumulation, and this is how we show it. You can see if I zoom in, for example, D1, what does it mean? You can see D1, it goes from high snow, depreciates as you go away from the higher roof, and it goes to normal. And look at this arrow. So I'm gonna show you. Look at this arrow here. So this arrow here, it simply shows you where do we apply the snow drift. And if you look at the 3D, I think it's obvious. The snow drift will take place all around the high roof. Okay. And then now, what is D1? So some of you will ask, Tahir, where is your KBA? So that's kind of a very, very typical representation on the drawing, where we don't say the numbers on the drawing. We use this fantastic option. And this one is called schedule. Okay, guys, look at this. This is a fantastic invention, and I will show you why it's fantastic for us. So you can see here, I never say on the drawing, I never say, this is 2.59 or 1 kBA, or the distance XD is equal to 3 meters, rather than putting everything in a schedule. And I will tell you why. So for example, what's D1? So you go from D1, you go here. So this D1. And what this tells you, that D1, the maximum snow is 3.82. It goes from 3.82 to 1 in a distance 4.75 meter. Okay, so you find here drift length, and this XD, and this S of 0, and this S of XD. If you wish, I can write it for you. So this number is your X sub D, and this number here is your S of XD, and this number, finally, this number here is your S sub 0, which is right next to your high roof. Okay, so guys, why this is important, I will keep saying this for the entire class this year. Schedules are amazing invention, because simply it saves a ton of effort when it comes to drafting. Okay, for example, let's say the engineer has done one mistake, or the architect, for example, change the value for the elevation of the higher roof. So the engineer will go ahead and simply recalculate the drift. But when he wants to, or she wants to change the drawing, simply he doesn't have to go and touch the plan view. The plan view will stay the same. However, they have to change the number in the schedule. This is a fantastic, again, invention. We will keep saying about schedule in columns and beams, because simply otherwise there should be a lot of errors. if you don't use schedule. Okay. Now, final comments on this part here. This is a snapshot from the they call it node page. Guys, I know that in other classes with other teachers, they show you some structural drawing, and any structural drawing, it starts with a few pages. Those few pages, it can be 1 or 2 or sometimes 10 pages. We call them node pages. Node pages. They don't have any drawing. They don't have any like elevation or plan view. They have notes. And please, if you have a pen, if you have been sleeping for the last 15 minutes or so, wake up. Okay? Node pages are super, super important. I don't know how many times I tell you that I got some questions from the contractor, and my response is read the node pages. On the node pages, there are so many important information. This is only a snapshot of part of the node pages, talking about design loads. And I kind of highlighted few things here to just grab your attention here. Look at number 4. So under number 4, it's talking about importance category. There's something we study and we know about it. And because this is an expansion of police station, then it is post disaster. And what does it mean? It means anytime I do the snow load, simply I need to multiply all the numbers by, the snow numbers by extra 25%. And you can see that down here. So down here, there's another box. It says IS is equal to 1.25. Also, SS is 1.2 and SR is equal to 0.1. Can you tell me why it's not 1.1? Anybody knows why this is not equal to 1.1? The SS? Sleepy.
It's post-disaster.
Because it's not in Calgary.
Thank you. Who said the first one?
I did. Brody.
Who's that?
Brody.
Okay, look at this. I'm not trying to make fun of you, so don't be offended, please. Okay. So the thing is, when we think about importance category, okay. So here we go. The 1.25, because of the importance, is 1.5 is here. My question was about the SS and SR. It is 1.
Sorry, I thought you were talking about IS. My bad.
Sorry, I have to make it clear, okay? Anyway, so 1.2 and 1.1 is because here we go. This a Medicine Hat police service, so it's not in Calgary, and that's why we have a little bit extra snow. Okay. Now, guys, so far I have finished all I want to say about the snow. And again, as I said, this will allow you to finish 95% of the assignment. The last part is here. So I'm going to talk right now about rain, and sometimes we call it the bonding load. And this is according to Alberta Building Code 2019, item 4.1.6.4. Now, really, I wanted, because when I talk about snow load, I want you guys to feel it, right? So I'm about the rain load. So I kind of found like 4 different interesting pictures or photos, and those photos on the top left here, there is a normal like a pitched roof, and it has kind of corrugated sheet. And when it rains, what happens? You can see there is no reason for the rain to stop and stay on top of your roof. So simply the rain will fall and then will fall off your roof. It means we get no extra load. Please pay attention to the following. You can see here, I have on the right side, top right, there is a little roof where there was some rain and there was little parapet. You can see, I think it's kind of blue. And you can see very clearly that the roof has collected some rain. And I think obviously that this roof has to be designed for such load. Otherwise, it's going to collapse because water, it has a weight, and simply it adds to the loads on top of your roof. Okay, one more picture here on the bottom left. There is some also, it's raining right now, and you can see the roof is collecting some water. However, look at this portion, black thing on, here we go, this thing here, okay? So this thing here is simply a drain, a roof drain, and simply the water will go, and then the roof has to be sloped in a way So the water will run from all the roof to the drain, and then simply the drain will take the water and put it in the sewer system, okay, or the drainage system, okay. But I want to share with you something. This picture is a very nice picture because look at inside the drain. You know, we get here the fall, and in fall, what happens? You get some tree leaves, and the tree leaves will fall off, and with the wind, probably it will go to the top, and then with the rain, it goes, and probably sometimes it blocks your rain, your drainage. So there's something we will talk about it shortly. Also on the top roof, there's a guy and there is lots of rain, and the guy is using a brush or something to, you know, kind of push some water off the roof. Okay, not really practical. There should be a drain, because if this guy is sick, what happens? You know what happens, huh? So anyway, what I said, I'm trying to say here in this picture is that how do we drain the water? So how do we do that? There are several ways. For example, in houses we do this guy here. So we slope, and then at the very end we have like the rain gutter, and the rain gutter will take the water with the slope as well, with the gravity, to down spouts, and it goes to down water to the side of your house, and then it goes off your building. Okay, so that's one way. The other way is this here. So this building here also, we have to slope our building, our roof, and then we provide in the parapet. You can see here there is a little parapet, and so because we have a parapet, so if we simply don't allow water to drain off, so again the roof will be loaded. So what we do is we make a box, we kind of make a hole inside the parapet, and this hole, it's called scupper. So the scupper will simply take the water again one more time downwards, downward spout, and here we go. So we get rid of the water. Okay, you know what, like this is typical condition in the house. Like in a house, that's what we do. In a warehouse, we have a parapet around, and probably we have to keep our building pretty. So this not really very pretty, because simply you're adding your drain to the outside, not really very pretty. So I'm going to show you right now. The last one is, this is very typical for warehouses. For example, if you go to like Superstore or IKEA, all those are warehouses, and this is exactly how they do it. So what they do is they have a drain inside, and typically the drain will be very close to a column, and then there's something called the rain water leader. Rain water leader. I'm going to write it for you here, guys. It's called rain water leader, and typically in the drawing you'll see RWL. So whenever you see the word RWL, it means rain water leader. It's just a vertical pipe that simply takes the water from the drain and put it in the sewer system. Okay, and typically it cannot be like in the middle of the warehouse. So simply we make those close to the column, and you will see, if you pay attention, sometimes we box around the column so you don't see it, but sometimes you will see it. You will see a pipe that goes next to the column of the building. Okay, so that's how we simply get rid or drain. Now, as we said in this picture here, you guys see there is a possibility. There is a possibility of this drain to be clogged. You know, with the dirt, with the leaves, so it could be clogged. So that's why, because there is a possibility that could be clogged. Here we go. So the code has a big statement about the rain. Okay. So I will give you 2 minutes. So I'll let you read my slide. It's a slide you can see on my screen. It is about what the code is saying about the rain load. Okay, so a couple of minutes. I will start the discussion one more time at 8:37. Okay, guys, I'm here one more time. So one thing you need to pay attention to, we refer to the snow load by S, and we will refer also to the rain as S. Okay, so both of them, we assign them letter S. And then on statement number one, it says, and it's obvious, it depends on the shape or the geometry of your roof. Sometimes roof houses, they don't collect, if they are not flat roof, roof houses, they simply don't collect any rain. We don't have to think about rain for houses because simply it has a high angle and there is no parapet and simply the rain will fall off. And that's what it says on the first part of statement number one. But the other thing is, okay, now I'm a designer. I'm trying to design my building. I'm trying to make my building strong to withstand the rain load. How much? How much? So the code is very specific. It says is the resulting from 1 day rainfall. So I'll tell you what is the meaning of 1 day. It means if your structure has a roof and this roof has all the reasons to collect rain, unlike the houses. And again, since we agree that there could be a dirt, there could be some leaves which potentially will block the drain. So the assumption here is it's only 1 day. Otherwise, it will be overkill. And so maybe after 1 day, there will be somebody on top of the roof. They are going to inspect and then simply clean the drain. So the code is asking only for 1 day fall, 1 day fall. So that's number one. Number two, it says here, sentence number one, apply whether or not the surface is provided with means of drainage. So if you have a drainage system or if you don't have a drainage system, then so don't say I have a drain, so it will be fine. No, whether you have a drain or you don't have a drainage system, then you also must consider 1 day, one full day of rainfall. And I will talk about this shortly. What does it mean 1 day? Now, the other thing is, which is good news, you don't have to design for rain and snow together. So rain and snow need not to be considered on the same time. And that's exactly, it makes sense because in winter we get snow and in a complete different time we get rain. They don't happen together. And which means we have to design the roof for either snow or rain, whichever governs. Number four, which is really very important, it says wherever scuppers. And what are scuppers? Scuppers are little opening in the parapet to allow some water to go off the roof and then go into the downspouts and simply get rid of the water. So in case if you have scuppers, then and also the shape and the deflection of the building will allow for rain accumulation, then the loads due to the rain shall be the lesser of 1 day fall, 1 day rainfall, or a depth of water equal to 30 millimeter above the scuppers level. I know so far is not really very clear, and I will show you when we start our numerical example. I'll show you how do we apply this statement, okay? But for now, let's move on to our next slide. So guys, back again one more time to our lovely table, which is about talking about climatic information or climatic design data. We used exactly the same table, probably one class or two classes ago, where we found the snow load to the right. So there is two columns, and we have a header snow load. It's over there, huh? So it's here. This is over like the snow load in KBA 1/50 SS and SR. So we used those columns before. Today, when we talk about rain, it's a different column. And again, one more time with Corwin, you used the wind load. So anyway, I kind of boxed those like columns for you. This one is 1 day rain. One more time, we say 1/50. What does it mean? It means it will happen once every 50 years that the rain will be with this intensity in millimeter. Okay, so in Calgary here, there is one time over 50 years it will rain, and the depth of water will be 103 millimeters, so 10 centimeter of rain in one day. Okay, now I'll show you how to apply this one, and we have here a rain load calculations. Okay, so as I said, things will initially look dry, and I cannot follow. But as soon as we do a numerical example, then I think things will get better. Okay, so I give you here kind of a roof in Calgary, a roof in Calgary. So the roof in Calgary, the dimensions. I want you guys to take a look first on the roof. So the roof has it looks like it has higher roof and lower roof. How do I know that? How do I know that this is a higher and lower roof? Simply by looking at the elevations. So I provided here some spot elevations. So spot elevation, there is the portion that I already highlighted or shaded. The corner is 8,000, so it's 8 meter. And as I said before, the way we collect the rain is by sloping the roof. We slope the roof to a low point. So you can see here is my low point. So this is my low point, and all the corners are higher by about 150 millimeter, because the numbers here is 8,000 and the number here is 7,850. So you can imagine that all those corners, 1 and this corner 2 and this corner 3 and this corner 4, their elevation is 8,000, and then everything is low, go to the low point here, and this is where we place our drain. So here we go. So if I write text here, this is drain. Okay, so drain will be placed at the lowest point. Now, how about this one here? This one here, this one is a higher roof. How did I know it's higher roof? Look at the numbers. You can see the corner is 12,000 and the low point is 11,850, which means this point here for the drain is lower by 150 millimeter from the corners. Okay. Now, the way we do it is, if the building is Calgary, I said here building is located in Calgary, and this means rain intensity is 103. Very simple. How? You look at the table. It's here. In Calgary here, the rain intensity is 103, and it's 1 over 50. It means probability level 1 time over 50 years. Now, let me ask you, if I'm saying that in Calgary here, it will rain, the intensity of the water depth is 103. How much water the low roof will collect? Okay, one more time. In Calgary here, it rains 103 millimeter in that day, in the worst day in the 50 years. In that day, how much water the lower roof would collect in that day? Not very difficult. What you have to do is, excuse me?
I was going to say 139.3 meters cubes.
It's on the slide. Thank you so much. So guys, here's the thing. You have to multiply the area of the roof. So it's not very like a super science. You multiply the area of the roof and you can see dimensions. Dimensions are here. So here is my first dimension, 52 meter. And here is my second dimension, it's 26 meter. If you just multiply 52 by 26, which is the dimension of the lower roof, you multiply by the rain intensity, you simply get this number, and this number is what the lower roof collects in one day, in that day. Now, I know some of you will say, okay, you know what? If my roof is flat, let's assume, if my roof is flat, it means it doesn't slope, which is not the case, by the way. So it really slopes because we want all the water to go to the drain. But I'm trying to get you into my point. I'm asking you, if my roof is flat, completely flat, 100% flat, okay? And then you go into this day and you have a ruler and you measure the amount of water, and assuming the drain was plugged, how much would be the water depth?
10 millimeter.
10 millimeter?
It could be 0 or.
No, I'm saying the drain is clogged. Like, that day, let's have assumption that, this one day in 50 years, You know, nobody cleaned. There is lots of dirt, and the drain was clogged, like it doesn't allow water to run off. My question is, and
103.
oh yeah, sure, yeah, that's true, because simply my roof is horizontal, and it rains 103, then I get 103. If I have my ruler on that day, I place my ruler on the roof, I get measurement of water depth of 103. Okay, now, which is not the case, by the way. Why it's not the case? Because my roof is not really perfectly flat. I slope my roof in a way that simply allows water to run to the lower point. I want to say, guys, I'm not stopping here. Gonna get something like off the topic. It's very important. How do we slope our roof? How do we slope our roof? There are two methods. One is to make the structure itself, like the beams and columns, of the same height, but it changed the depth of the insulation. And this will give me my slope. Okay. The other method is you use exactly the same thickness of the insulation, but you slope the structure, which means some columns will be tall and some other columns will be short, and my beams will be a little bit sloped. Which one do? We do the second one. We always change the slope of the structure, not the insulation. Because it's very difficult, by the way, to shave the insulation and make here 4-inch insulation here, and here is 3 inches. It doesn't work. It's not really good. It doesn't work. So what we do is we fabricate our members. If it's steel building, we change our columns in a way that allows the drainage with the given slope. Now let me go into more detail. So let's say, you know, I know that my roof is not perfectly flat. So how much is going to be my water head on the roof? Is, you know, when you think about it, you will see this is pure. Next is pure mathematical discussion. The next part is pure mathematical discussion. Okay, and I try to make some colors so you guys can read it and feel it and understand. Okay, so guys, as I said, the yellow, you can see the yellow is here. This, I'm referring to this part. This part here, the yellow part here is, as you can see, this kind of a 3D of the lower roof, which shows you the higher point here. So this is the higher points, and the lower point here is here. Okay. Now, in math, what do we call this thing? I guess only if you are Egyptian you should know.
A pyramid.
A pyramid. Are you Egyptian?
I got Egyptian family.
Okay.
But I mean, I mean,
because you know what, like Egyptian, they do nothing, just build pyramids. That's what we do, day and night. Okay. Okay. So guys, listen. In math, this is something we call it pyramid. Yes, true, it's pyramid. And so I'm asking you, like, look at the situation right now. I said if my roof is flat, that's very simple, because simply the water head will be 103 millimeter. However, once I slope my roof a little bit by giving a low point and high point, it looks like the math will not be as easy, but it's not very difficult. I'll show you. So let's say now my roof, we agree that is going to collect 139.3. Anybody is following? My roof 100% will collect this much. Now, when we talk about this much, so what you have to do is you need to find the volume of the water to fill the pyramid. The volume of the water to fill the pyramid. You can see I show the pyramid here in 3D and in my cross section. So what you see here is a cross section. So this is the elevation of my pyramid. You can see it's inverted pyramid. So the base on the top and then the vertex is on the bottom. Now, how do we know the height of the pyramid? How do we know the height of the pyramid, which I mark it here as 150? It's as simple as look at the plan view and read the numbers. You can see the high point and the low point. The difference is 150 millimeter, and that's where I got the 150. Now, is that difficult to find the volume of the pyramid? Okay, if you are good at math, you will know that the volume of the pyramid is 1/3 the area of the base times the height. The volume of the pyramid is 1/3 the area of the base times the height. And if you apply this, what is the base? It's simply 52 meter by 26. 1/3 is constant, and then 0.15 is the height, because it's here in the elevation, huh? And again, on the plan view, the difference in elevation between 8,000 and 7,850, this is 150 millimeter. So guys, look at the number. So really the amount of water that fills the pyramid is 68.9. However, my roof is collecting more than 68.9. What this means, it means I still have extra water. So this water will rise, will keep rising, and you can see it generates this blue volume. Okay, it generates this blue volume. Now, what you have to do is, how can I find the X? So I want you guys to look at the X. What is X? I'm going to probably zoom to the side. So X is the height from the high point on the pyramid to the level of the water. Not very difficult, huh? Not very difficult. If you are good at math, you will know what I mean, huh? So what you have to do is, number one, you have to see how much water left between the 1 day rainfall and what fills the pyramid. So if you get the difference, and so the difference is a volume, and then you go ahead and divide the difference in volume by the area of the base, which is 52 times 26, what you see is you get here a 52 or 0.052 meters, which is a 52 millimeter, which means what happened is, if this building in Calgary and my drain is clogged and it rains in that worst day in 50 years, guess what? The water will rise and will go to a level of 52 millimeter above the high point. Are you following, guys? I need to hear some voices or noise.
Yes.
Okay, thank you, sir. Okay, now, so but what happened is the code says, if we go back to this statement here, the code says here, where scuppers are provided, and let's assume in this problem that we have a scuppers. So where the scuppers are provided, then you need to consider the minimum, the minimum of 1 day rain or maximum 30 millimeter above the scupper level. Okay, and that's why, let's go back to this problem here. Based on our calculations, in that day, we know in Calgary, the water will rise and become 52 millimeter, which is here. The 52 millimeter is here. Okay, will become 52 millimeter. But if we have if you have some scuppers, so the code says maximum is 30 millimeter. What does it mean? It means if it's 52, then you have to make it 30, okay? Because the scuppers will allow some water to drain off some water from the side of the building. For sure, if you have no scuppers, so there is no way to go, it means you have to consider the total 52 millimeters. This is only where you have some scuppers, okay? Now, we're done. By the way, we're done. So here's my diagram. I'm going to show it to you one more time. So let's say this building has a scupper, and which means my water level maximum will rise above the high point by 30 millimeter. Now, so what is the total water head? So at this point here, the water head is equal to 30 millimeter. How about the water head here? The water head here. Simply, it is your pyramid height, which is 150 plus the 30 millimeter. Then the total water head is 180. Guys, maybe in other classes, probably with Fraser, huh? With Fraser, we talk about water head. It's pressure, right? Water head. But can we convert this into a pressure? It's very, very simple, okay? All you have to do is just find the water head at point A, which is the low point, and then find the water head, the pressure at point B. Very simple. What you have to do is you multiply the water head times the specific weight of the water, which is 9.81, okay? And that's where you get the kVA or kilonewton per meter square. Remember, this has to be in meter. I know that my calculation so far is 180, but here on this side, it's in meter. Why is that? Because the 9.81 is meter cube, huh? So it has to be consistent units. And that's why you can see here my water pressure in on the low point. The water pressure on the low point is 1.77 kVA, and then on the high point, we get 0.29 kVA. Okay, so the water pressure here at this point is 0.29 kVA. Here is 1.77. Now what you have to do is just print or plot a rain diagram on your roof, same as we've done with the snow. You can see here is my roof one more time. And I draw a baseline. You can see I draw a baseline. Here's my baseline. is here. So that's my baseline. And in two direction, you can see here is my another baseline in this direction. And then what happened is we know that my my water head here or pressure is 0.9 kPa. And then at the low point, here is my water pressure. It's 1.77. You draw the same diagram in both direction in X and Y. And here we go. This is called drain or bonding load diagram. Any questions so far? Any questions so far?
Taher,
Go ahead.
if like this roof looks like it's designed to have that drainage go through the middle, like in through the building, correct?
Yes.
So then wouldn't be like putting the scuppers on the side be kind like somewhat useless, and like you're only design like those are basically like a safety mechanism in case it rains like a stupid amount in that day?
Kind of agree. Kind of agree, but the it depends on the scuppers elevation. Like I know what you mean. Like I really know what you mean. I want to find the good answer for you, to be honest. Like, you know, like what you're saying, if you kind of imagine the slope of the roof, and if you put a scupper.
Yeah, like how is it ever going to exit the scuppers, because it's sloped so much that it's just going to go towards the middle through the building.
But the scupper is added not for the drainage of every day. For every day is going to go through the drain. The scupper is put is only for emergency for that day where the drain is clogged, and then the water will go to the scupper.
Okay.
Does it make sense?
Yeah, that makes sense. Yeah.
So it's kind of emergency. It's kind of a second run, so the water that can run off of the drain. Second, you know, kind of a second or emergency exit for water. Okay. Now, guys, with that, I finished this part, and by now you're able to finish 100% of the assignment. And if you go check the assignment, let's check that. Hopefully, I didn't do any mistake for that. The assignment, the due date is 1 week from now. And as I said, it's already released a couple of days ago, so it means practically it is more than 7 days. But I understand your frustration, and I want to help you out. And you can see I give you 1 full week from the time I finish all the materials. Okay, so let's see. So here is my class, and let's go to the assignment. So the assignment, and I guess I have to show it as a student. So student. Okay, so assignments. We have 2 assignments, and it's due to October 7, and I think October 7 is simply the next Wednesday after the class. So it will be at 10 a.m. That day. Really, if you want, and I need to hear your voice, I can extend this one, but not really to the next day, to the midnight of that day. Is that something is going to help you?
That would be
Yeah,
good.
Yes.
absolutely.
Yeah.
Yes.
Sure, sir, sure, no problem. Okay, so I'm going to do that. So finish the students, and let's do it now so I don't totally forget. So assignment, and then edit guy, this guy, edit. See, it's very simple, huh? Just we have to be in a good term. That's it. That's all you have to do. Restrictions, and then this is gonna go to midnight, and this guy is gonna go to midnight. Very simple, right? And then here we go, save and close. The assignment is due to Wednesday, 11:30. But please, I don't want to get an email saying, you know, I couldn't, or please do your best to do it in the time, okay? Otherwise, it creates a lot of work for me for administrating things beyond the D12. Okay, guys, with this being said, I'm gonna break. So I'm gonna see you guys here 9:10. Thanks.